I'm going to first of all talk to you about what are the key cycle chemistry features for optimum cycle chemistry control, and of course for HRSG reliability. This will include the optimum cycle chemistry control and the treatments, and then I'll also show you some of the latest international statistics on a large number of plants, which were previously presented, Bob, at the European HRSG forum that Bob and I run usually in May each year. And the statistics were also developed for a chemistry meeting in Australia in May. So this is the first time we've shown them in for the HRSG community here in HF. So first of all, just let's have a look at what we consider are the important aspects for optimum cycle chemistry control. And these are not really ours specifically, and all of them have been around for more than 25 years as the key features for optimizing the chemistry on combined cycle plants. And some of them still are not fully adopted. So the first thing is that we like to see that the chemistry is designed to address all the possible cyclochemistry influenced damage and failure mechanisms. And I'll outline the important ones for you. In the condensate and feed water of these combined cycle HRSG plants, we like to have oxidizing treatments. And that means we call that AVTO, all volatile oxidizing. That means not having any reducing agents. And this is to control and to prevent single phase FAC from taking place. We also know that we need to add ammonia or an amine and oxygen control by minimum air in leakage. And most recently, we have to have very careful application of FFS because these film forming substances do not have the same level of understanding as the previous chemistries, which have been around for 25 or 30 years. For the LP evaporator, we can operate, depending upon the design of it, we can operate with all volatile treatment, or we can have an additional alkali added. We prefer it only to be trisodium phosphate and or sodium hydroxide. The second important chemistry control parameter is to optimize the pH to minimize iron in the cycle, but optimizing pH is the thing that controls the two-phase FAC. This is very important. We like to see the HP drums and the HP evaporator tubing should be red with minimum internal deposits, which will result if you have that optimum chemistry control that I've just indicated. And of course, we have to have the guidance level of continuous instrumentation, and this should include steam. Steam is probably the most missed aspect of the monitoring for combined cycle plants. And also, it's not considered adequate to control HRSGs just with grab samples. And you'll see that many plants are controlled in this way. So this is the chemistry that's been around for 25 to 30 years, some of these things. But despite this, we find that around the world, we have continuing cycle chemistry influence damage or failure in HRSGs. And this slide just indicates some of them for you. The chemistry influence tube failures, of course, are the most important, with the leading tube failure being flow accelerated corrosion. And this is the leading HRSG tube failure. And this was confirmed, although we already knew it, in the last HRSG forum that we had. Bill Kitterman was presenting on his repair work, was one of the leading repair people and companies in the US, and he indicated that flow accelerated corrosion keeps him busy and was the leading thing that he had to deal with. The other one, of course, is under deposit corrosion. And whereas 10 or 15 years ago, it could have been related to phosphate or caustic, now essentially it's only due to hydrogen damage. And we see hydrogen damage, unfortunately, all over the world. The other aspect that we see is corrosion product transport. This is total iron due to inadequate feed water and lower pressure circuit chemistries. And of course, if you have elevated corrosion product transport, you will get deposition in the HRSG HP evaporators. And this is the incipient situation for these under deposit corrosion mechanisms. The importance of having an air-cooled condenser in a combined cycle is very important because if the chemistry isn't right, we'll have very large levels of iron. And of course, most recently, with the new operating mode, this measurement of the corrosion products becomes a little bit more difficult for frequently and fast start plants. We also have problems on the steam turbine, which seem to be increasing, and these relate to stress corrosion cracking and corrosion fatigue in the phase transition zone of the low pressure turbine, all initiated at pits on the surfaces. We also see deposition in the LP, which is one of the things that we don't want to see. So there's 3 slides now. I'm not going to take too much time on them, just to show them to you, to illustrate that last slide. First of all, flow accelerated corrosion, and we find that this represents something like 40% of all the tube failures in HRSGs. I have to say that we don't know that exactly because there's no statistics, but just based on our surveys that we've done and in meetings like this where we have a show of hands. And so this here just shows 2 examples of 2-phase FAC in the low pressure evaporator, typical appearance here. And this little slide over here illustrates the mechanism. And if anybody's interested, you can go to this recent review of FAC in the PP Chem journal. And the second failure mechanism is hydrogen damage, which I mentioned. You can see the typical characteristics here. The heavy deposits on the internal surfaces of the HP evaporator, the severe corrosion, as you can see here, multi-laminated scale, and if you do the analysis carefully, you'll find levels of chloride at the metal oxide interface here. This mechanism has been understood for many years, and still is occurring in combined cycle plants in HRSGs. And the third one that I just wanted to highlight was the steam turbine damage mechanisms. These in green here, down here, are cycle chemistry influenced. You can see the cracking by the corrosion fatigue or stress corrosion cracking here, cracking in the attachment, in the blade profile, and across the blade profiles here. All of these mechanisms are initiated at pits, as you can see an example on the surface here, and this is what we need to try to prevent happening. So all of these mechanisms that I mentioned are cycle chemistry influenced. This means that the basics of cycle chemistry control are not being applied. We refer these to, for more than 10 years now, internationally, we refer to these as repeat cycle chemistry situations. The original paper, if anybody wants to read it, is down here at the bottom. And since this original paper in 2008, the data, the 2021 data that I'm going to show you, which is accumulated from assessment at over 250 plants worldwide, continues to confirm that all of this failure, or all of these failure mechanisms that we've just seen, and damage can be directly related to plants operating with multiples. That's 2 or more of these RCCS. You can read them here. I'm not going to go through them because I'm going to give you a couple of examples to illustrate what constitutes having a repeat cycle chemistry situation or the lack of having that basic chemistry control. And for combined cycles and HRSGs, Bob and I summarized the results in this PPChem paper in 2019. And all of these papers that are noted at the bottom here for your reference are available on the HF site, and Scott will be able to tell you exactly where that is later. But you can get these are freely downloadable. And so this large amount of data has been collected from detailed plant assessments using this repeat cycle chemistry situation analysis. And for combined cycle plants, this is the number of them, this is the different manufacturers that we've looked at. These are the sorts of assessments that we've been made to derive this data. So we've done total HRSG assessments. Bob and I typically would do cycle chemistry, FAC, and look at the thermal transients. And we might just do cycle chemistry assessments by themselves or optimization for a plant if they request that. Very often for FAC assessments and air-cooled condenser assessments. Of course, tube failures, mechanism and root cause. And these assessments have been made in a very wide range of plants. Chemical plants, oil and gas plants, desalination plants, LNG plants, alumina refinery plants, so it's a very large and comprehensive database. And so what I wanted to do now was just spend a few minutes just to itemize for you for a few of these repeat cycle chemistry situations in a plant, what constitutes a plant having one of those. When we go to a plant, what constitutes it being included in the database as a repeat cycle chemistry situation. So I'm going to give you 3 or 4 or 5 examples here. So the first one is on corrosion products. So that's the measurement of total iron. And as I already mentioned, you'll see that this is going to be covered in detail in part 2. I just wanted to whet the appetite here by just showing you a few of the things that are the most common. So plants, when we visit plants, the corrosion products would be not known, or they'd be too high, above some local guidance achievable value. Local guidance, that can be, it can be any of the organizations that develop local guidance for you. But not only this, we noticed that in many cases the techniques that are used are not correct and would only result in measuring the soluble corrosion products, which is not total iron. So the most common one is no digestion, is not digesting the particulate, and Ken will deal with this in some detail in the second presentation. Samples are sometimes not representative, and the biggest issue there is that the chemists or the technicians or the operating people take the samples at the same time of the day or the shift each day, rather than taking them when the unit is at under the same condition. And then there's a couple of easy items that you can see. So if you look at the steam and water, or the wet rack, which it's called in the southern hemisphere, sampling troughs, they need frequent cleaning. And if you see black deposits in the sampling troughs on AVT, this is not good. Or if you see red deposits on units that are AVTR, they shouldn't be on this treatment anyway. But if you see the red in there, that's also not good. So Ken will talk about each one of these in a little bit more detail. And this is just an example. I don't want to spend too much time on it, but I already mentioned that guidance organizations around the world typically have achievable total iron copper limits. This just happens to be from the IAPS one. And so here you would look for the feed water. If it's operating on ABT, you'd want the total iron to be less than 2 ppb. For drums, HRSG evaporators or drums, on any of these treatments that I mentioned, or volatile, phosphate or caustic treatments, you'd hope that the total iron would be low, as indicated here. And for those units with air-cooled condensers, we like to see the total iron, if there's a filter, being less than 5. If there isn't, then we'd hope that it was less than 10. So these are really achievable values that plants with optimum level can easily achieve. The second item, the second category, is on the HRSG HP evaporator deposits, and some of the things that indicate that this is a repeat cycle chemistry situation for a plant are given here. So first of all, probably the most frequent is that samples have not been taken, and the plant might have ended up with hydrogen damage or large amount of deposits causing problems. There's no knowledge of the deposit and the deposition rate. Samples are taken but not analyzed comprehensively, whereas this is quite well understood what has to be done. Deposits are excessive, are not linked with the chemistry of other parts or FAC and other parts of the plant in the low pressure circuit and the lower pressure circuits. And so here on the bottom right hand side is an example of what we like to see in an HP evaporator tube, nice and red and smooth. And if we have that, then we know on the deposition map, then when we measure the deposit loading, it would be down here in this green area, indicating, first of all, optimum chemistry, and secondly, that the unit doesn't need to be chemically cleaned and is not at risk of having hydrogen damage. Now, the next item is on continuous online instrumentation, the next repeat cycle chemistry situation. And again, this is going to be the topic covered by Kirk in the third part of today's activities. And so what we would typically see is we have low levels of instrumentation compared to an international standard or the local guidance. And most often we find that that case or cation conductivity, as it used to be called, and sodium on steam circuits is missing. And very often the conductivity on the makeup line to the condenser is also missing. We quite often find that these are not alarmed. Many are shared and not or never switched. And one of the bad things is plants rely on grab samples to control the plant. You know, 1 or 2 times a day, 1 or 2 times per shift, or once a week, or something like that. And this isn't adequate. And many of the plants, when we make a visit, are out of service, not maintained or calibrated. And then if you look down here at the bottom, you'll see some subset of that. So the average for combined cycle plants is about 58% of what should be there for that particular HRSG. We see very few plants with 100%, and we see quite a few having no instrumentation, like I indicated before. And Kirk will cover each one of these items in half an hour. The fourth item, or the fourth category, is repeat cycle chemistry situation is on drum carryover, and so we very often find that this is not conducted since commissioning, even though this is one of the things that's a really key part of phase transition zone failures and damage, and cracking and deposits. And many plant people are not aware of the simple process just shown here, where you could measure the carryover against the drum pressure, and hopefully it would be below this line. And you would do it about every 6 months to make sure that there hadn't been a problem in the drum. or even on new units. We find even new units straight out of the construction, just after commissioning, we find that the levels of carryover are very high. And so this is the fourth item. And the final item that I just want to mention is on what we call not challenging the status quo. And for this to be a category in your plant, we find that many plants are operating with the same chemistry since the plant was commissioned. There's no chemistry manual for the plant, or the chemistry manual isn't assembled by the plant, or could be assembled by an external chemical supplier as compared to company guidance. Continue to use the wrong phosphate or phosphate treatments, or continue to use reducing agents. As we've indicated, we don't like reducing agents or oxygen scavengers. Many of you will call that in combined cycles. And in all ferrous plants. No severe questioning of what proprietary chemicals are being added, incorrect or outdated guidelines, and the most recent one, of course, is that no changes have been made for frequent or fast starting plants. And so these are some of the things that contribute to these features having an RCCS. And so the final thing that I want to do before I hand it over to the other two is just to let us have a look at the latest statistics. And Bob and I have been collecting these statistics for quite some time in the assessments that we do. You can see the time period down here. And so these are the categories, all of the categories. I only covered just a few of them for you. This in the green here is the data from the combined cycle plants, and this is the data from fossil plants. But you'll see they're very similar, and so this just provides us an indication of the ranking of those basic cycle chemistry features which are not being addressed properly in HRSG plants. So you'll see the leading ones are corrosion products. Here, these numbers represent the percentage of plants that have this problem or have the problem that I indicated earlier. So corrosion products is very high. Online alarmed instrumentation is right here as well, and drum carryover. And then you would have not challenging the status quo. So you can see this is why we chose today to talk about corrosion products, to see if we can improve the understanding of the basics, just the basics of measuring total iron in the cycle, and why we chose online instrumentation. There is a good thing on this slide, and that's these arrows that are pointing downwards. We have noticed that in the last 5 years, there's been an improvement, a general improvement in the overall statistics, which are indicated by these arrows. So this is the introduction to this session. I just wanted to make a few concluding remarks here. First of all, is that we have, for the HRSGs combined cycles, well-established and understood chemistries, which have been in existence for 25 to 30 years. So this is the all volatile treatments, the oxygenated treatment, phosphate treatment using only TSP, caustic treatment, and an understanding of the phase transition zone, failure and damage in the steam turbine. There are some simple rules for optimum chemistry control. I gave you those on the second slide at the beginning, but as we've seen, the repeat cycle chemistry situations exist as shown, and these relate to the very basics of these chemistries, and of course can lead directly, as I've indicated, to plant reliability and performance issues. If you have recognized any of these in your plant, as we've gone through here, or as you see something in the next two presentations, you should try to have them eliminated, because if you have more than two of them, they'll link together, and the database tells us that will result in failure and damage. So you can turn that around and actually look for these repeat cycle chemistry situations and see how many you have, and see what the importance is of the cycle chemistry within your plant. So ensure that these simple rules are applicable to my plant, and most importantly, as Ken will indicate, conduct a comprehensive monitoring review using total iron to ensure these rules are applied, and that repeat cycle chemistry situations are not allowed to continue. We use the total iron to try to indicate whether the plant has optimum chemistries or not. And this is most important right now, because over the last probably more than 5 or 6 years, as film forming substances, film forming amines and film forming products have been introduced into these plants, we recognize that these are not as well understood as these chemistries up here that we've indicated, and need this monitoring process to make sure that there's going to be no problems. I have to tell you that there have been problems. We've run 4 international conferences on film forming substances, and there are quite a range of problems in these plants. And of course, now we have the operational changes of frequent and fast starts, and so if we have those, it's also a good idea to monitor the total iron.